let's look at another very useful trick called the phasor trick from this particular chapter, simple harmonic motion. Remember, of all the tricks that I've told you, this is the most powerful of all, because here you can visualize motions. Here you can also visualize how two SHMs, two separate SHMs will look like, and how do you solve the problems which involve two SHMs two SHMs happening at the same time. Let's look at a very simple problem to understand how phasors work. So this y is equal to a sin omega t is the equation of your SHM, right? And if I ask you how much of time does your particle take to go from root 3a by 2 to a, what will your answer be, right? So what you'll do is you'll take root 3a by 2, you'll take sine inverse, get the value of time, you'll take a, you'll take sine inverse, get the value of time, subtract those two times to get the particular time taken to cover this particular displacement from root 3a by 2 to a. But there is a very simple method to do it. What you can do is put your particle here on a circle of radius equal to amplitude. Remember, in phasor, your radius of circle equal to amplitude. So this is your a. This is your a. Now, as you can see, your y is a sin omega t. So if I say that your particle your particle is rotating with omega. Remember, your phasor's rotation angular velocity is the frequency of your SHM. The frequency of your SHM is the frequency, angular frequency at which with which your body is rotating. This omega and this omega cannot differ, they have to be the same, right? So let's say after a certain instant of time t, this thing has come here. So let's say it has come to omega t, right? Omega t, this will be the angle, right? So if this is your a, then the projection on y-axis will be a sin omega t, right? That means the projection of this body's motion on the y-axis represents this SHM, right? Very clear. This is moving, this is having omega t here, and your y is equal to a sin omega t. That means this particle is moving like this. I put a torch from this side, and whatever I see on this is nothing but this motion, right? So what I'm being asked about is, initially it's at root 3a by 2. So let me draw that particular case. When will it be at root 3a by 2? When this particular angle is 60 degrees. This angle is 60 degrees. Then the projection will have a sin 60, that means root 3a by 2, right? And then finally your particle has to be at a. If it has to be at a, then the angle has to be 90, right? Angle has to be 90. So first your particle was here, right? Now your particle is here. How much of angle has it covered? 30 degrees, right? 30 degree. 30 degree I can write in terms of radians as pi by 6, right? Pi by 6 radians. So my angle is pi by 6 radians. My angular velocity is omega, right? I need time. So what I know is theta is nothing but equal to omega t, and t is what I need, and that will be equal to theta by omega, so which is pi by 6 divided by omega, right? Divided by omega. And if you know the time period, you can use that as well, right? Yeah, pi by 6 by omega. This is your answer, right? In case you need, you can also do it in terms of time period. So you can replace omega with 2 pi by t. So t is equals to pi by 6 divided by 2 pi by t. So when you cancel this out, t will be equals to capital T by 12. So a lot of problems can be solved using this phasor concept if you understand what's happening, how the projection and all works. I hope this problem was simple enough for you to get a feel of what phasor trick is. But a lot of problems, instead of going into trigonometry, getting inverse solutions and trying to solve the problem, you can always use a phasor trick to do it much more conveniently and faster. That's what is required in the examination as well.